In this next video, we will get into why bands spread as they move throughout a column. In other words, we recall that when we first start, our solute might be in this compressed band here, but as time goes on and it flows through the column, it starts to spread out more and more, which is what ultimately leads to us having this peak width by the time it leaves the column and is detected. Now, we've already covered this idea a little bit in a previous video, but we're about to get way more in depth, starting with the concept of diffusion. I'll preface this with a question. If I were to spill a cup of water on the table, what would happen? Well, there we go. That water spreading out is diffusion. And this will happen in a column as well. Over time, particles will just naturally spread out from one another in each direction in the column, like so. Okay, so even as these solute particles are being flowed through the column in this direction, they are just naturally spreading out every which way in this process known as diffusion. And the longer it takes to get these particles out the column, the more time the particles have to diffuse from one another and cause that band to become wider. So let's write this down. First, let's just label this section as why do bands spread? Why do bands spread? And we just covered one of three major reasons. Diffusion. Solute molecules diffuse away in both directions. Solute molecules diffuse away in both directions. This is specifically called longitudinal diffusion, but we don't need to know that. The more time it spends in the column, the more diffusion occurs. The more time it spends in column, the more diffusion occurs. And part of what controls the time that a solute spends in the column is the flow rate of the actual mobile phase. How fast are we pushing that mobile phase through the column, which in turn relates to how fast is it dragging those solute particles along with it. So a slower flow rate corresponds to more time spent in the column. So underneath this part, let's write slower flow rate. And then parentheses will note that we're talking about the flow of the mobile phase. And so there's this inverse relationship between the extent of peak broadening and flow rate, which has the symbol lowercase u. Okay, so that's flow rate. Typically, we will see units of milliliters per minute. Don't worry so much about that. Just understand the concept of a flow rate. The faster this is, the faster that we move solutes through a column, the smaller the broadening, the less time those solutes have to diffuse away from each other. So that's one of our three major reasons for bands spreading out. Our next one is called finite rate of mass transfer. Once again, I'll show you a quick visual and then we'll write some notes. So here's a visual from the book. It's rather confusing, as is the description. I think this concept is most easily illustrated with an analogy. I'll start by saying that basically there's always part of the solute that's more engaged with the stationary phase and a part that's more engaged with the mobile. So imagine a shoe that is stepped in gum. When the shoe was still on the ground, all the gum was wadded up in this nice compact form, but then the shoe starts moving. And let's imagine this gum represents our solute band. The shoe is the mobile phase, and the sidewalk is the stationary phase. Makes sense, right? We can see here, the part of the gum that's attached to the sidewalk is lagging behind the part of the gum that's attached to the shoe, and then the rest of the gum is just stretched out in between. That's the concept of the finite rate of mass transfer. Some of your solutes will be more engaged with the stationary particles in the column, and some will be more engaged with the solvent that's flowing through the column, i.e. our mobile phase. And for reasons I won't really get into, the broadening effects of this are increased if we increase the flow rate of that mobile phase. So let's write some notes. Reason 2 for band spreading. Finite rate of mass transfer. Finite rate of mass transfer between phases. The idea is that the solute particles that are in better contact with the stationary phase will lag behind. We'll just write solute in better contact, solute in better contact with stationary phase lags behind. In this case, broadening is worse as the flow rate speeds up. Broadening worse as flow rate speeds up. In other words, broadening is directly proportional to flow rate. Now let's take a step back, look at these two mechanisms for broadening, and realize that we have an issue. Okay, first, let's recall that we don't want peak broadening, right? Broader, wider peaks lead to worse resolution. This in turn leads to a more difficult, if not impossible, analysis further down the road. And so we have these two different mechanisms, and we've discussed a way that we can potentially cause the broadening to decrease. But what's the issue when you look at both of them at the same time? The issue is that the way that we can control the extent of peak broadening is by adjusting the flow rate. But unfortunately, we will have opposite effects on the two broadening mechanisms. If we were to speed up the flow rate, we will decrease the broadening caused by diffusion, because there is this inverse relationship here, right? Larger number here, smaller number there. But unfortunately, that will increase the broadening effects from finite rate of mass transfer effects. Increase this number, increase this number. And so there's always some happy middle ground, some optimal intermediate flow rate to balance these opposing mechanisms. So let's write that note. And we'll star this, and we'll write optimum intermediate flow rate to balance opposing broadening mechanisms. Optimal intermediate flow rate to balance the opposing broadening mechanisms. To balance the opposing broadening mechanisms. Figuring out what that flow rate is part of a chromatography experiment. Let's quickly illustrate this concept more clearly with a simple visual. Let's say that we're flowing our mobile phase through a column at some slow flow rate, don't worry about any specific number. And this causes the diffusion broadening for our solute particle that's being moved through said column to be rather wide, at least relative to what we'll be seeing later on this slide. And so the half width we'll say is 6 units long. However, at this slower flow rate, we'll say that the mass transfer broadening effects are rather small, since this is directly proportional to flow rate. And so let's say that the broadening effects at the half height from this mechanism cause the peak to expand by a width of 1.25. So between the two broadening effects, the total width will be 7.25 at half height. So that's just the peak width with both of these effects taken into account. Now, let's speed up the flow rate to a speed that we'll label medium. And let's say that at this speed, we've caused both of these broadening mechanisms to change by a factor of 2, but in opposite directions. This goes down by a factor of 2, this goes up by a factor of 2. This ultimately leads to a less broad peak. And the reason why is because the diffusion is being decreased by an objectively larger amount than the mass transfer broadening is being increased, right? We can see this goes down by 3, and this goes up only by 1.25. And so our total peak width at half height is 5.5. So things have ultimately gotten better by speeding up our flow rate. We have reduced diffusion broadening more than we have increased mass transfer broadening. But let's keep speeding up and get to some flow rate that we'll label as fast, where once again we decrease this by a factor of 2 and increase this by a factor of 2. Now the reverse situation has happened. While this is getting better, it's only going down by a total of 1.5. However, this is going up by 2.5. And so there's a net increase in broadening compared to the medium flow situation. Our half width is 6.5 in this case. So the best peak width, the most narrow peak width we could achieve was somewhere in the middle. Because eventually if we keep on speeding up, the improvements we see from diffusion broadening are more than canceled out by the worsening mass transfer broadening effects. With that, we can summarize this slide with the following statement. If you continue to speed up the flow, the effectiveness towards reducing diffusion broadening goes down, while increases in mass transfer broadening more than cancel out the benefits of speeding up the flow rate, and vice versa. So the optimal broadening reduction is always found between a minimum and maximum speed, which you basically wrote previously. And so, like many things in life, the middle ground is where we should strive to be. Now we have one more major broadening mechanism to cover, and it's called multiple paths. And this arises in any column that is packed randomly with these stationary particles that we've been discussing. When we have this random distribution of particles, it'll turn out that some solute particles just happen to have an easier path through this maze of particles than others which have to travel, say, like this, and they're just going to take longer to get out. And we actually discussed this concept in an earlier video when I gave that hokey hurdle analogy, although we didn't call it by this name. So now let's write this down officially. Multiple paths. Our third reason that bands spread. So multiple paths occurs in any column packed with particles. Occurs in any column packed with particles. Some flow paths are longer than others. Some flow paths are longer than others. And in this case, the broadening is independent of the flow rate. It doesn't matter how fast we try to move those solutes through the column, the maze is the same no matter what. And so we'll note that broadening is independent of flow rate. Is independent of flow rate. And there we have our three major reasons for peak broadening.